Hello everyone, today we will present our comparative study between LSTM and transformer encoder models for the age-in-use text classification test. Instead of just asking which model is better, we focused on analyzing how they differ in performance, convergence, and error patterns under identical training conditions. Our presentation consists of four parts: introduction, experimental setup, result, and conclusion. We compared the sequentially processing LSTM with the parallel processing transformer encoder. Both were trained entirely from scratch to ensure a fair comparison. Our research addresses three main questions. First, which model achieve higher final performance? Second, how do they compare in data efficiency when scaling the training data? And third, what are their error behaviors at specific class boundaries? For our dataset, we used age news, which consists of four perfectly balanced classes. This balance prevents any performance distortion. For pre-processing, we used a custom rules-based tokenizer to handle use-specific patterns. The labels were mapped simply from 0 to 3, ensuring all four classes were treated on a completely equal footing. Crucially, our vocabulary was built strictly from the training set. This prevents any data leakage into the validation or test set. Regarding the architectures, both models use embedding dimension of 128. But the most important controlled variable here is the parameter scale. Both the LSTM and transformer were matched to exactly 2.82 million trainable parameters. We also used identical training setups such as Adam optimizer and 15 epoch budget. By strictly controlling this variable, any performance gaps we see will directly reflect the structure differences of the models, rather than hyperparameters. Let's look at the result. We scaled the training data across 25%, 50%, and 100%. A distinct pattern emerged on the 100% test set. The LSTM holds a slightly edge in discrete matrices, achieving about 91.8% accuracy compared to the transformer's 91.6%. However, the transformer consistently recorded noticeable lower cross-entropy loss across all data ratios. This means while the LSTM is slightly better at final class decisions, the transformer produces much better calibrated probability distributions. These learning curves highlight their different convergence behaviors. If you look at the LSTM's loss curves on the right, its validation loss begin to rebound halfway through the training, indicating slightly overconfidence in later epochs. In contrast, the transformer's validation loss decreased much more stably and peaks at a later epoch. To summarize, the LSTM runs quickly to reach strong accuracy, while the transformer converges slower but with great stability. To understand their errors, we visualize token class associations. The main observation here is the heavy lexical overlap between the business and science tech boundaries. For example, tokens like Netflix or Intel provide strong tech cues, but they frequently co-occur with financial terms like market or quarter. In these ambiguous scenarios, both models struggle to make clear distinctions. This observation is confirmed by the confusing matrices. Both models perform exceptionally well on distinct classes like sports. However, the vast majority of misclassification for both models occurs right at the border of business and science tech. In conclusion, under a fair from scratching training setup, the LSTM slightly outperformed in accuracy, while the transformer excels in loose calibration and stability. Ultimately, the failure modes for both models were quite similar. They were bounded by the same lexical ambiguities at specific class borders, rather than their own struggle limitation. Thank you for listening.